In this lecture, we will discuss Dalton's law of partial pressure, which is basically concerned with the pressure of a gas when the system contains mixture of gases. Suppose we are having a container enclosing three gases represented in red, yellow and green color. If these gases are non-reacting, then pressure of each gas would be unaffected from the pressure of other gases, and it would be the same if it was enclosed in a single gas system. And pressure of each gas in a mixture of gases is called partial pressure of that gas. And total pressure of the system would be the sum of individual partial pressure, right? So Dalton's law can be stated as total pressure exerted by a mixture of non-reacting gases is the sum of their individual partial pressures. This statement can be mathematically written as Pt is equal to Pa plus Pb plus Pc. And if the system contains more than three gases, their individual partial pressures will be simply added up to make the total pressure of the system, right? Now let's elaborate Dalton's law with an example. Suppose we are having four cylinders, each of the volume 10 decimeter cube, and three of them enclose three gases, hydrogen, methane, and oxygen, and their pressure are 400, 500, and 100 torr respectively. When these gases are transferred to a fourth cylinder, this mixture is formed, and according to Dalton's law, pressure of the system would be the sum of partial pressure of hydrogen, methane, and oxygen. As the pressure of the hydrogen, methane, and oxygen are 400, 500, and 100 torr respectively, adding these we will get 1000 torr. So total pressure of the system would be 1000 torr. Students, according to general gas equation, PV is equal to N times RT. From this equation, we can get the value of P as N times R times T divided by V. Now put the value of pressure in the Dalton's equation. N will be replaced by N hydrogen, N methane, and oxygen, while the other quantities would be the same. Now separating the variables and constant terms, we will get N hydrogen plus N methane plus N oxygen times RT divided by V. From this equation, NH2 plus NCH4 and NO2 is clearly showing that these are the total number of moles involved in the system. So this can be replaced by NT, which means the total number of moles in the system. So PT is equal to NT times RT divided by V. So this is the general gas equation for mixture of the gases. And from this equation, we can clearly say that pressure is directly related to the number of moles. By increasing or decreasing the number of moles of particular gas in the system, the partial pressure of that gas would also be accordingly increased or decreased. And ultimately, total pressure of the system would be increased or decreased accordingly. Now let's calculate the partial pressure of the gases. This was the equation for total pressure of the system, and from this equation, P can be replaced by A, B, C, or the particular gas which is involved in the system, and number of moles are also replaced accordingly. And for gas A, it would be PA and NA. Remaining terms would be the same. And for gas B, it would be PB and NB. Now let's divide the equation for gas A to the equation for mixture. This will be the answer. RT by V would be cancelled out. Students, Na by Nt is the mole fraction of gas A involved in the mixture. So this factor can be replaced by Xa, where Xa is the mole fraction of gas A involved in the system. So partial pressure of a gas can be found by knowing mole fraction of that gas and multiplying it with the total pressure of the system. So this is the equation for gas A, and for gas B, partial pressure of gas B would be equal to mole fraction of gas B times total pressure of the system. Now let's have an example. There is a mixture of hydrogen, helium, and methane occupying a volume vessel of volume 13 decimeter cube at 37 degrees Celsius and pressure of 1 atmospheric. The masses of H2 and helium are 0.8 gram and 0.12 gram respectively. Calculate the partial pressure in torrs for each gas in the mixture. In this statement, temperature is 37 degrees Celsius, which should be converted into the Kelvin by adding 273. So temperature would be 310 Kelvin, right? And volume of the vessel is 13 decimeter cube and pressure applied to the system is 1 atmospheric, right? Now let's find the number of moles of a mixture. According to general gas equation, PV is equal to nRT, and from this equation N is equal to PV by RT. Now putting the data in this equation, N would be equal to 0.51 moles, right? These are the number of moles of mixture. Now find the number of moles of individual gases, because we have to find the mole fraction first and then we can find the partial pressure of the individual gases. Number of moles of hydrogen would be equal to mass of hydrogen divided by molar mass of hydrogen, and it will give zero point 0.4 moles. Similarly, for helium, mass of helium is 0.12 gram according to this statement, and molar mass of helium is 4 gram per mole, and this will result 0.03 moles. And from the data, we can find the number of moles of methane by subtracting the number of moles of hydrogen and helium from the total number of moles, right? And it will result 0.084 moles. Now number of moles of hydrogen, helium and methane are found. Now let's find the mole fraction of hydrogen, helium and methane. For this, divide the number of moles of hydrogen to the total number of moles and it will result 0.784 for hydrogen. Similarly, for helium, it would be 0.058 by dividing the number of moles of helium to the total number of moles. For methane, it would be 0.164 by dividing 0.084 moles of methane to the total number of moles of the system. Now, mole fraction of hydrogen, helium, and methane are found. Let's put this data in Dalton's equation. Here, partial pressure of hydrogen would be equal to mole fraction of hydrogen times total pressure of the system. It will result the same 0.784 atmospheric, but the answer is required in torr, and 1 atm is equal to 760 torr. Now multiply 0.784 with 760 torr. It will result 595.84. Now the partial pressure of hydrogen is 595.84 torr, right? Similarly, for helium, it would be 44.08 torr. By multiplying 0.058 with the 1 atmospheric, it will result the same answer, and then multiplying with 760 torr. Similarly, for methane, it would be 124.64 torr. Right, so in this way we can find the partial